Okay, thoughts I have about Module 6. Module 6, we call it, let's see here, exponential and logarithmic functions. Here's what's on my mind about that. And logarithmic, hold on. Functions, just pretend like I said functions or equations or something there. Okay. So far, we've done a lot. We've analyzed a lot of different things that happen. Recap. Some unknown number, and it was always like, well, if you times it by this and minus that, and it equals something, can you figure out the missing number is? This is a scribble, not a number. Anyway, and you're like, well, if it says times 3, then I can divide by it. If it says minus the 5, then I can plus to get rid of the 5. Minus 5 means plus 5. I can get the x by itself, no big deal. And do the plus 5 on the other side. And if you have a times 3, then at some point we'll probably divide that 3 and undo it. And anyway, that was the basic foundation for all this stuff. And then we got, as time went by in college algebra here, we got more and more intense. We had linear functions like that, where it was just x to the 1 power. And then some other functions that got more and more involved, where it would be like x to the 2 and x to the 3, x to the 4, etc. Polynomial functions like we had mentioned before. And then x to the 1, of course, and then x to the nothing was when it was a constant number, where it was just a number, no x's at all. And then so that was polynomial functions. Then in rational functions, we were like, well, what if we went into the negative powers of x, and that was kind of weird. And finally, in module 5, we got into this idea about radical functions, we call them. Radical functions and equations that started to put the gaps in between powers of x. And that was a whole weird idea, about like, how do I have an x to a power that's not a whole number of x's, And that was weird. And we had certain things like x to the 2/3 power or whatever, 2/3, pretend like it says that. X to the 2/3, x to the 3/4, x to the 5/8, and then all kinds of powers that are in between all these whole numbers, And so it seems like we've covered the whole gambit of basically everything. We have positive powers, negative powers, 0 power, and now powers of x that are in between all these other whole numbers, filling in the gaps as much as we want to, pretty densely. It'd be hard to imagine other places to go with that. And there are some other places to go, though. And so here's one of the other places to go. Here's something weird that was on my mind. Check this out. It doesn't even, okay. So here's the thing. As complicated as all that has been, with all the things that we've studied so far, it seems like, well, in order to get a function or an equation or something, something mathematically intense enough to go beyond all of these things that we've already studied, it would have to be pretty amazing. But I was just thinking about that, and just here, dig this for a second. If you had a piece of paper, suppose you had a piece of paper and you started to and you were like, I'm going to fold this in half, So you fold the piece of paper in half, you put the top piece on the bottom piece, and then you have a piece of paper that's, it's cut in, or not cut in half, but it's folded in half. It's not as big as before, and it's 2 layers thick, Okay. And then, as you may have done this before, let's try and fold it in half again. And so then maybe we'll put the left-hand side over the right or something. And now we have these 2 layers from the left folding on top of the 2 layers on the right. So we have 2 going on top of 2 over there. So then we have something that doesn't take up as much space left and right that way. But now it's 4 layers thick, and you can start to see it happen. There's line 2, and then 3 layers, 4 layers, pretend like I drew it well. You got 4 layers thick here. That is pretty poorly drawn, but whatever. Now we got 4 layers thick there. So this is 1 layer thick, 2 layers thick, then 2 on top of 2 is 4 layers. And if I were to cut this thing in half, fold it in half once again, and put the bottom on top of the top, or the other way around, and I fold this thing up, well, we have 4 layers here going on top of another 4 layers. And so then I guess you have 4 on top of 4 would make this thing, it'd be 8 sheets thick. And I'm not going to draw that one. Just imagine it was 8 sheets thick. Okay. And it'd be all dinky in the other dimensions. Okay. Well, we're noticing this. If we were to start keeping track of what's going on, and I was like, well, the number of folds that we've done, folds, versus the number of layers thick, there's obviously some kind of a doubling process here, twice as much, twice as much, twice as many, you know. So if I were to keep track of the number of folds when we had 0 folds and 1 fold and 2 folds and 3 folds and 4 and 5 folds, well, I guess we could find a pattern here. Let's see, if we had no folds, that's what we started with before we folded the thing, and it was just 1 layer thick. Then when we folded it once, we put the top down to the bottom, we put 1 on top of 1, it was 2 layers thick. Then of course 2 on top of another 2 became 4 layers thick. So with 2 folds, a second fold gave us 4 layers thick. And then if we did it a third time, we put those 4 on top of those 4, and it became 8 layers thick, you know, whatever. And then of course you can see the pattern here is just 8 plus another 8, or 8 times 2 or something would be 16, and 16 plus another 16, or 16 times 2 would be like 32 pages, etc. And it would keep on going in this pattern, you know, if we wanted to continue that on. Seems like it would be no big deal to imagine how that would go, just times 2 times 2 times 2, for as long as it was physically doable. There's a lot to be said about that too. Okay. So it seems like the relationship that's going on is, well, if we started to try and look for the pattern, it just looks like, well, it takes something times 2 times 2 times 2 times 2 times 2. So surely we have a shortcut for doing a bunch of times 2s, you know, and I think that we do because we've run into this kind of thing before. That's just 2 to some power. But I guess what's different here is that the power keeps changing, you know? And so maybe we could say it's like a 2 to the x power or something like that going on. Matter of fact, if we were to use the variables that we most sensibly would come into with f and l here, with, you know, folds and layers, I guess what we could say is something like the layers depends on the number of folds, you know? And so if we were to view layers as being a function of folds, we could say L, or for layers, equals probably something like, I guess it would be 2 to the power of the number of folds, and I'll put 2 to the f there for folds. I think that works. Let's just see. Okay. The only thing that looks a little bit weird is, what do you do when you plug in a 0? Is that really going to work? You know, because 0 folds was 1 layer thick. It wasn't 0 layers thick. Hold on. Okay, I paused it for a second, but you know, whatever, because something made a noise. Anyway, so okay, we were like, well, does 0 work? Is that going to work? And actually, it kind of does, because if I plug in a 2 for the number of folds here, 2 to remember, and this is not obvious by any means, like why in the world would this be the case? But it is true. 2 to the 0 is 1, you know? So if I plug in a 0, I actually do get a 1. And then 2 to the 1, if I plug in a 1, then my output should be 2, because 2 to the 1 is 2, you know, etc. I think it all works. Let's see if it works with one of the bigger values. If I do a 5 in there, then 2 to the 5 is, yeah, 2 to the 5 is 2 times 2 times 2 times 2 times 2. And that is 32. That's pretty cool. Okay. So it looks like we have some kind of a relationship. We've described this pretty well algebraically. Okay, here's why I bring it up though. What you'll notice is different about this kind of function versus the ones that we've seen in the past is that, well, in all those ones, we kept on having huge powers of x in the, you know, in the positive or negative direction, and even fractioning powers of them. And it got super weird. But it was always that the unknown number, we had some unknown number x, and then we did some power thing to it, you know? We had like, say, unknown number, and then you take it to a 5 or to a 4 or to a 3 power, to a 7 power, whatever it is, to a -1 power, to a negative this power. Doesn't really matter. It was always unknown number to some particular power, you know? And now what we're seeing is a different story. Instead of saying unknown number to a particular power, we're saying take a particular number to an ever-changing power, you know? It's the power itself that's changing. And this presents a whole different kind of function for us, because now we're in a world where it may be hard to get the x by itself. And so let's look at that for a second here. Matter of fact, let's get a new page. Say I had a function that looked like ours. We'll keep 2 as the base number for now. Y equals 2 to the x, or even, you know, forget y. Let's not even think of it as a function for now. We'll just do some basic equation thing. And we'll do 2 to the x equals whatever. You know, say we did 8. That's easy enough because we could guess our way to that one. 2 to some power is 8. Well, that's 2 times 2 is 4, and then 4 times 2 is 8. So there's 3 of them. So the x should be 3 here. You know, like we can tell that x is 3 just by guessing, sort of. But what you've noticed is that there's no algebraic way to get there. Like then that becomes a problem if you run into a problem that's a little bit tougher than making a 2 into an 8, you know, because we'll check this out. Okay, erasing. Okay. Weird. Let's try it with the problem that we have here. Let's see if we can get the x by itself. You know, thinking of every trick that we've had so far, all the different tricks we've had, we were like, well, okay, remember like before, dear diary, let's think this through. The way we always got x by itself was, well, whatever you're doing to it, I'll undo that. So if I have 5 times my x equals some whatever number, 1,000 or something, well, if it's times 5, then I'll divide the 5. Bam, you know, whatever you do, I'm gonna. And if I had an x minus 2, then you're like, well, minus, I'll undo the minus with a plus, you know, whatever. You have 1,000 and then plus the 2, whatever. It doesn't really matter what we do to it. Even when things got weird in polynomial land and beyond, it was like, well, okay, if I have x and then it's to some weird power, I know how to undo that. If I have x to the 3 equals some big old number, then I could be like, well, I know how to undo a 3 power. I'll do a 3 root or a 1/3 power or something. And then like, I always have an inverse operation to undo whatever's been done. And that's, I think, what is different here, because you'll notice whatever's being done is actually what we don't know. You know, instead of saying there's some number, I don't know what it is, but I do something to it, I can undo that. Well, here, okay, I started with a 2. That's not a mystery. What do I do to it? Well, I don't know. I don't know what I've done to this 2. I took it to some power. I don't know what power. I don't know what I've done. And it's supposed to get me to an 8. In my mind, I know it's 3 just because I know how to guess there. But I don't know how to get the x by itself. I don't know how to algebraically undo this process. A times makes divide, a power makes a root. So the only thing that came to mind is like, well, okay, if I did it to the x power, I could do the x root or something, you know, which, I mean, I guess you could sort of do as long as you know, we're careful about this and that, but it doesn't help because you don't know what root you're taking to either, you know, so the x to the root of 8, it doesn't really mean anything, you know, an unknown root. So this is problematic for us. And that's why we have a whole new module about this stuff, because these are the first time, excuse me, this is the first time we're running into a problem in which we don't know how to undo what's been done. We can't algebraically get that x by itself, and we need a new idea here. We need a new idea in particular because, well, what if they do get worse than this one? And you can't guess your way to the answer. And that's what kind of motivates these problems. Check this out. What if I gave you 2 to some power, and then it's supposed to equal like 17, you know? Well, good luck with that one, you know? I'm thinking over here, powers of 2, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. That comes pretty close. 2 to the 5 is way bigger than 17 already. So we're like, well, I don't know, 2 to something is supposed to be 17. It's just got to be barely bigger than this. So if I were to guess, I'd be like, I don't know, 2 to the something barely bigger than 4, but not close to 5. You know, so if I had to guess, my guess would be something like 4.1 or something, you know, ish. And of course, that's a whole other thing, you know, wrapping your mind around like what is a 4.1 power of something. That's more what we talked about in the previous module. And so this puts us in a funny spot where I'm just guessing numbers, and that's probably not accurate, you know, although I think it's a pretty good guess. But anyway, so now algebra guessing. Kind of like now this puts us in a position to be creative. We need to find some new creative way to handle things. And here's what matter of fact, maybe we could revisit 2 to the x equals 8, or here, we'll just start clean slate here. We know that 2 to the something is 8, that's 3. So if I were to just say, let's just start with the statement 2 to the 3 equals 8. And we'll take that for what it is, because 2 times 2 times 2 is 8. This is an identity. There's nothing, you know, variable to solve here. And we were to think through this, and I were to think through it as kind of like a function in a way, it's like a machine for a second where I was doing things to a 2 and I was getting outputs, like we did 2 to the x equals 8, and then 8 was the output, and I figured out 3 was the input we needed to make that. Okay, this 2, we call it the base number. That's not really changing. There's not much really action going on there, but maybe here, we'll just draw up on the problem. And maybe we could think of it as like, okay, 2 is the base number no matter what, but what we do to it is something with a 3. And we could think of that as like the input of the function. If we do think of it as a function, then we'd be like, well, 2 to the 3 is what you do to it. So that's like the machine part, the input. And then 8 is what you get out of it, And so I take a 2, I do some 3 thing, and then I get 8 out of it, out of the machine. And if we're going to be able to figure out how to undo these problems, what we'll need then is an inverse. We will need an inverse function that switches these inputs and outputs like inverses do, We'll need some kind of an inverse function that backwardizes this process. So I could take something to do with the 2, and then we'll be like, I'll take something to do with the 2, and then we'll do an 8 thing with it, and then we will get out of it a 3 will be the output, somehow. That would be the idea, is that, well, 2 is the number I'm dealing with, so that doesn't change. But instead of doing something with a 3 and getting an 8, now we want to be able to do something with an 8 and get a 3 as an output. That way, the power, the exponent part, will be the output. And it would switch things up so that we may be able to get this exponent by itself. And that is where the world of logarithms come in. And this will be the key to us figuring out solutions to weird exponency problems like this one, where we were guessing at our answer, And so I'll go ahead and I know this is an intuition video, so we don't do a lot of nuts and bolts, but what that invites us into then is we define logarithms. And so logarithm, here's how we write that, was we'll say, well, log, short for logarithm, the base number was 2, so that's not changing, We're saying take the 2, and instead of doing a 3 thing, instead of doing a 3 thing to it, we'll do an 8 thing, Instead of do a 3, get an 8, we'll do an 8 thing and get a 3 as an output. So the 8 will be the input now. And then 3 will somehow be what we get out of it. And that's what we need to define. And here's what we've come up with so far. Base number is 2, that's not going to change. So we just say logarithm base 2, and then we'll say do an 8 thing to it. Log base 2 of 8 equals 3. And this is our logarithm way of saying that same thing. It still means 2 to the 3 equals 8. But now we have a different backwards way to think of it, of saying I take the number 2 up to an 8. This is the power that got me there. So 2 to something gives me the 8. 2 to what gives me the 8? 3 output. That's what we're thinking about in logarithm land. Is now 8 is the input. I take the 2, I do some 8 thing to it, and then what gets spit out is the power that got me there. 2 got to 8. This is the power that I took to get me there. So log base 2 of 8 equals 3 as an output. And now we have an inverse version of this funny exponency situation, And so finally, just to wrap things up, I guess what we would say is, so maybe now we have a way of I was going to say encountering, whatever, a way of solving. Yeah, let's keep things simple here, Adam, of solving equations like this, where we could be like, okay, well, maybe if I just rephrased it, log, the base number is 2, log base 2 of 17 equals the x, and now we're cooking with gas here. Now we have the x by itself, and we found an algebraic way to get the x by itself, to undo this stuff that we did by having a creative input-output switch inverse process. And now whatever log base 2 of 17 is, that's the x I was looking for. X is by itself. Algebraically, it's everything we wanted. And then, we used to do these on slide rules the way they used to do them. Nowadays, we just use a computer or a calculator to do them, log base 2 of 17. And there's some other ways to write that stuff too, if you need to do a change of base, this and that. Anyway, and so then I think if you do it in a calculator, my guess is pretty close. It's like not quite 4.1. So I'll put like wiggle equal. I think it rounds up to 4.1. But it's like 4.0 something, but it's 0.08 or 09 or 07 or something. And so it's right. It's certainly not exactly 4.1. It's 4.1-ish, you know? This is the idea about exponential and logarithmic equations. Exponential equations are this new world where we have the unknown is the thing that we're doing to a base number that we do know, you know? It's the power that we're taking something to that we don't know. And then we had these weird ideas about like, well, how do I deal with that algebraically? And so we had to redefine. So we had to define a new kind of function with new ideas here, because undoing something the way we normally do with an inverse operation just wasn't going to cut it. Cool. Anyway, there's plenty more to say about this stuff, but I think this is pretty good for now. Those are my thoughts on module 6.